Shall we start? All right. So today I'm going to start with a very concrete example illustrating what I was saying yesterday. Specifically, so yesterday I mentioned that you have the operad pre-Lie, which encodes the pre-Lie algebras. I remind the definition in a second. And inside, so it admits morphism from the operad Lie, sending the Lie bracket to AB minus BA, which corresponds to the fact that if you take a pre-Lie algebra, the operation AB minus BA satisfies its Jacobi identity. And I'm going to explain how that this is a PPW pair. I actually think that it's a very good example because I won't do all the computations on the blackboard, but at least quite a bit of the relevant computations you actually can do by hand, I think it's a very good illustration of what is going on. So first of all, I'll remind you that the pre-Lie algebras, also known as right symmetric algebras, are algebras with one binary operation satisfying the identity which is saying that the associator is symmetric in the last two arguments. So concretely, ABC minus ABC is equal to ACB minus ACB, and these algebras, appeared, some people will tell you that they are already implicit in the work of Arthur Cayley in 1860s, but that is close to truth, but perhaps debatable. But in any case, this specific identity appeared in several different areas of mathematics in 1960s, in work of Gerstenheimer on the formation of associative algebras, in work of Winbeck and Cajul on symmetric spaces. So somehow it's kept emerging in different places ever since. We want to focus on the pair pre-Lie and Lie, and so instead of looking at this particular identity describing the pre-Lie algebras, I am going to change the presentation of my operad to somehow highlight the presence of the Lie bracket. How do I do that? So the first step, I change the structure operations, meaning that I am going to consider the bracket A minus BA and the symmetrized product AB plus BA. Of course, it's a different. I'm going to write immediately the axioms that these two products satisfy, and somehow it's a completely different presentation of the same story, right? Because from these two operations, you can of course recover the product, the pre-Lie product AB, by taking the sum of the symmetrized product and the skew symmetrized and dividing by 2. So somehow we didn't really change much. We just modified the presentation of the operad, and so these operations satisfy the following properties. Of course, there is the Jacobi identity, which I'm going, well, for the moment, let me just write it like this. And two more properties. So somehow, let's just do some sanity check. So, of course, if we allow ourselves to use the symmetric group, then we just need to impose this right symmetric identity just as relations as a module over S3 are generated by this element. But what is the dimension of the vector space of identities of for Pauli algebras? I claim that it's 3 because you need to choose who goes on the first place, right? And this, so you have the identity ABC is equal to ACB, also BAC is equal to BCA, and CAB equal to CBA. So you have a 3-dimensional vector space of identities with 3 arguments. So we need 2 more identities, right? We already have the Jacobi identity. And to write an equivalent system of identities, we need 2 more. Well, let me write it. It will be a little bit heavy, but ABC minus 2 AC circle B plus yes, so everything throughout this course, unless otherwise specified, happens over field of characteristic 0. There are many different subtleties that emerge for positive characteristic, and I will only mention in the very end what can be salvaged. Most of the time it's characteristic 0. So A, B circle C plus A circle B bracket C plus AC B. So you see it's not as pretty as the original identity. So there is this and the identity 2 with where you swap B and C. These 3 identities are equivalent to the right symmetric identity for these new changed operations, for the symmetrized and anti-symmetrized product.
I don't understand what to do. It is not implemented.
Yeah. So that's something that this is some computation. So essentially, to obtain the identity like that, you take the right symmetric identity, you substitute instead of, so as I already told you, the right symmetric product is 1/2 of A circle B plus AB. You take this formula, you substitute it, you play around, and it turns out that
2 is Q-symmetric on A and C. Second.
Yes.
Symmetric on A and C.
Yeah. Well, it's some choice, so I prefer this choice for some reasons that will be apparent. But so in particular, this highlights, this identity highlights the well-known fact stating that if you have a right symmetric product which is commutative, it's necessarily associative, because somehow it's associativity modulo the Lie brackets. Right, so these are the, so now we want to, as I was hinting yesterday, and as I was telling in the mini course in Curitiba, we need to the advantage of shuffle operands that we can use in the universe of shuffle operands. We can do Grobner-Shashov basis, we can obtain normal forms, and so on. So let me the second step. So the first step, I changed the structure operations, and so I wrote the identities of my variety in terms of these new structure operations. The second step, I am going to translate it into the universe of shuffle operands. And for shuffle operands, we rewrite multilinear operations as combinations of trees. And so I'm going to use these two different things. So this 1, 2, I will put instead of bracket A1, A2, and this 1, 2 instead of the symmetrized product A1, A2. And let me draw some trees. So, and explain. So, first of all, the Jacobi identity in the shuffle world. So this is the shuffle Jacobi identity. And I remind you that shuffle trees, so I already immediately made some changes. So in shuffle trees, for every vertex of the tree, the minimum leaves of subtrees of that vertex must increase from left to right. So somehow here we had BCA, so if A is A1, B is A2, C is A3, I need to use this Q symmetry of the bracket, put the minimal argument on the left. And
So you have to remind this, have for people to accompany them. This is equal.
well, right.
It's the same because you use this.
Yes. But so my point is as follows. So in the world of shuffle operands, this element does not exist. So I was a little bit cautious about this. So I am doing rewriting on the level of multilinear elements so that something like that never happens, and this with the wrong order doesn't happen either. So let's do this little. Well, I mean, these elements actually I did some preliminary work when I wrote this. If you see that if A is A1, B is A2, and C is A3, so if they are just labeled by integers 1, 2, and 3 in that order, all these monomials here, all these multilinear operations, they already correspond to shuffle trees. I already did some preliminary work, so let me redraw this. Then minus A circle BC, it's this, minus bracket AB circle C, it's this, minus 2 AC circle with B, it's this, plus this, plus this, and plus this is equal to 0. I think that, yes, this is fine. And as I told you, the other one, I need to exchange B and C. So let me also write that. So here I exchange 2 and 3, and this is a perfectly valid shuffle tree. Here I exchange 2 and 3, it's not a shuffle tree, so I need to use the symmetry of the symmetrized product to write it as a shuffle tree. Here I exchange 2 and 3, this vertex corresponds to the Lie bracket, so I will earn the -1 sign. Here it's a perfectly valid shuffle tree like that. -2, 1, 2, 3. Plus I exchange, it's a symmetrized product, so this is fine. Plus 1, 3, 2, plus 1, 2, 3 is equal to 0. Voilà. So we have three combinations of shuffle trees. And so of course then we need to make some choices. We need to choose an ordering of trees. We need to say who is the leading term and then start doing the composition diamond lemma story to see what happens. Let me show you two different choices of, mention two different choices. So two interesting choices of leading terms. So perhaps, one choice is to say that trees that grow to the right are bigger than trees that grow to the left. That is one possibility, which is often very useful. So, first choice, trees that grow to the right are bigger. This is, one can formalize using one of the standard orderings of shuffle trees. So in this case, for the Jacobi identity, you have two trees grow to the left, one tree grow to the right, so this is the leading term. Here it's a little bit more intricate. So let's see, what are trees that grow to the right in all these combinations? So we have this.
Going to the left.
So there are two trees that grow to the left and one tree that grows to the right. Okay? Yes, yes. Yeah. Yeah, exactly. Yes. So here it's a little bit more interesting because this has this relation has three different trees that grow to the right, and this one has the three different trees that grow to the right, exactly the same trees. So we first need to do some kind of Gaussian elimination. We need to get rid of the coinciding leading terms. And trust me, well, actually you don't have to trust, it's very clear from what is here. If you can add these relations together and subtract them, and these trees are with the same sign, these are with the opposite sign. So you can, if you add relations and subtract relations, in one relation this will survive, and in the other this one will survive. Also, there will be the third one, but you can impose.
I don't understand. Can you repeat this side of this?
Yeah, so let me call this relation R1 and R2. I suggest to replace relations R1 and R2 by R1 plus R2 and R1 minus R2.
Instead of this,
Just this is one equation, this is another. You add them, you subtract them. If you add them, then this tree disappears. If you subtract them, then this tree disappears. And then also there is this tree, which if you subtract it disappears, if you add it doesn't disappear. But my point is that, okay, so there exists an ordering for which, well, the leading term of the Jacobi, the guy from the Jacobi identity, this one and this one are the leading terms of the system of three relations, the Jacobi, R1 plus R2 and R1 minus R2. Now, the composition diamond lemma would tell us what? That you need to look at overlaps of these leading terms and check that the diamonds close up. So there is this tree, which is the overlap of the Jacobi identity with itself, or the leading term. There is this tree, which is the overlap of this guy with itself. There is this tree, which is the overlap of these two leading terms. And finally, there is this tree, which is the overlap of this leading term and the leading term of the Jacobi identity. So there are four different overlapping guys, which you can rewrite in two different ways using the relations and see what happens. And a computation, which I am not going to do on the board, shows that in this case, all the diamonds close up. So somehow, in this way, you actually obtain a Grobner-Shashov basis. So, all diamonds close up. Somehow, okay, so, yes, 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 yes.
They should satisfy some axioms of order.
Exactly. Yes. Yes. So there exists. So in fact, so you know, I told you that trees go to the right are bigger because it's enough to somehow understand what is going on here. In fact, what I mean is that there exists a total order of all shuffle trees which is compatible with all the operations such that trees that go to the right are bigger. Yeah. Exactly. So,
and then respect multiplication. In this order, respect multiplication.
This order respect composition of substitutions of operations into one another. Yeah. That's the whole point. That we are no longer working with pre-Lie algebras. We're working with multilinear operations on pre-Lie algebras. And the only structure that we have is shuffle substitutions of operations into one another. That's a very important point. Now, the fact that we obtain a Grobner-Kirchhoff basis means that shuffle trees which do not contain fragments like that are normal forms. Let me call, let's see, star, are normal forms. This, okay, I can already erase this. This is not yet will.
Infinite number of observations possible. We always get a finite number of normal forms.
Well, the point is that in every arity, for every number of arguments, the total number of shuffle trees is finite. So somehow this is a very important distinction. So the whole story is very similar to Grobner-Kirchhoff basis for associative algebras, where you look at subwords of words and so on. But over there, a Grobner basis it not only can be infinite, here in total a Grobner basis also can be infinite, but the point is that you cannot really see whether it a good analogy is as follows. If you are working with an associative algebra whose relations are homogeneous, then for every length of the element, the part of the Grobner basis is finite, so there is some kind of convergence thing. And here it's kind of similar. For every arity, for every number of arguments, the Grobner basis is finite, and so there is, if you want to know what is happening for multilinear operations with 8 arguments, you can actually compute it. It's an algorithmic question. Now, so we're looking at normal forms that do not contain these fragments. So this comes from the Jacobi identity, meaning that you rewrite all multilinear Lie monomials as left-normed products. And there are these things which are a little bit harder to understand what is going on. But what I suggest is the following. So let's look. So there are all normal forms. And inside them, let me give you a very useful illustration. Inside them, you have normal forms with this at the root. Or if you want, normal forms, so normal monomials for which the last operation that you use is the symmetrized product. I claim that let me call all these n, this n prime. Observation. You can obtain n as by substituting n prime inside Lie monomials. That every normal monomial every normal monomial is some Lie monomial of normal monomials where the last product to use is the symmetrized product. Why is it so? Because if you have, what could possibly go wrong? Something that could possibly go wrong is that if you have a Lie bracket, you substitute here or here the symmetrized product because you are taking things from L prime. And if all of that was a normal form and that was a normal form, the only way for things to break is because of this substitution, right? If you already know everything about normal forms. But these are the leading terms. They don't create problems like that. If you substitute the symmetrized product into the Lie bracket, it's not the leading term of our Grobner basis. So maybe let me write it n Lie, yeah.
You can reduce to one.
No, I'm just saying that this is a real and honest equality of the sets of shuffle trees, that every irreducible element is uniquely represented as an irreducible Lie element composed with an irreducible element like that.
That all you in this way you obtain normal. Why every normal not can be obtained?
Because a normal form, well, it's a shuffle tree. If it has the symmetrized product at the root, it's already in N prime. If not, you just take the biggest Lie component around the root. And so, for example, I don't know, this and so let's see. So for example, 1, 2, 3, 4, 5, 6, 7. This is a normal. This is a normal form, right? It's not. It doesn't have any fragments of this sort.
No, Sensei, but assume you have without symmetry, just for instance, you have this. You see.
Yes, you are right. You are right. You are right. Thank you. I should also, of course, add to it just the trivial tree corresponding to the identity operation. So yes, you are right. So every normal form is a Lie monomial of things, each of which is either a letter or a product, a symmetrized product of something. Yes, thank you. Yes, you are right. Thank you very much. Now, how to use this observation? Corollary. That the operad pre-Lie, the species pre-Lie is can be written as, well, strictly speaking, we apply the forgetful functor. Pre-Lie is Lie U circle X, shuffle circle X. So this formula is, yes, so where X is the ordered species of normal forms, ordered species spanned by n prime union with this identity, which, if you think of it for a second, means that in the world of shuffle operades, at least, the shuffle operad pre-Lie is free as a left Lie module. So in the world of shuffle operades, pre-Lie shuffle is free as a left Lie-U module. This is, of course, not what we wanted. We wanted to prove that it's free as a right module for PBW property. But how to use the... So first of all, as I told you, freeness of a module is something that you can check in the universe of shuffle operats. So this implies that pre-Lie is free as a left Lie module. So we can go back to the world of operats. And an immediate consequence of this result is another very cute fact about pre-Lie algebras, that every free pre-Lie algebra is free as a Lie algebra. Of course, on infinitely, even if you start with a pre-Lie algebra on one generator, you will get a Lie algebra on infinitely many generators. But somehow this result, so pre-Lie isomorphic to Lie circle some x, you apply it to the species epsilon EA, so which is A concentrated in arity 0 that we discussed, and you get pre-Lie of A is isomorphic to Lie of x of A, which shows that the pre-Lie algebra generated by a vector space A is isomorphic to the free Lie algebra generated by the vector space X of A. So this X, the space of generators of the left module, computes the generators of the free pre-Lie algebra as a Lie algebra. Now, okay, so so after all, our motivation was PBW pairs. So,
maybe the result that it is PBW pair, because it's free,
it's free as, we proved now that it's free as a left module. For PBW pair, we needed to prove free as right module. So let me show to you how to adapt it to do the PBW pair. So I erase this first choice.
not by mod pair.
No. Well, I mean, those are, yeah, it certainly is not free as a bimodule, so yeah, so you have a bimodule structure, but for some purposes, for results like that, you use the left module structure, for PBW, you use the right module. Yes. So the second choice, I am going to say that trees, to begin with, I am going to say that trees that contain more symmetrized products are bigger. And among them, well, okay, so in the Jacobi identity, all trees contain zero symmetrized products, so we still need to choose the leading term somehow. But here, the trees with maximum number of symmetrized products are these. So, for example, we can take. So, for example, for example, there is an ordering such that no, 1, 2, 3, 1, 2, 3, and 1, 3, 2 are the leading terms. So what do we need to do now? There are several different overlaps. So there is one overlap of this tree of the leading term, new leading term of the Jacobi identity with itself. And in fact, there are 6 different overlaps between these guys. So each tree like that, where you have 1, some A2, A3, A4, is an overlap of these leading terms, because, well, here we have basically both possible orderings are present. So here we have, so there will be 6 overlaps like that and 1 overlap like that. We do some calculations. In this case, we don't have a Grobner-Kirchhoff basis. Some diamonds don't close. And we obtain new relations. I'm not going to write them to you explicitly, even though once I did it by hand on for each overlap, just 1 sheet of A4 paper, not too heavy. So obtain 3 new relations with the leading terms one, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Of course, these leading terms, they form overlaps with these guys. So we need, in principle, we need to continue computing. We need to continue checking the conditions of the composition diamond lemma. That I didn't want to do by hand. So here there is a funny shortcut. It's possible to check that for the, so now we have the 6 leading terms we have. We get n to the power n minus 1 normal forms in RTN. So you look at shuffle trees that do not contain this fragment, this fragment, this fragment, and which do not contain these 3 fragments. And it's possible to do some combinatorics and establish that the number of normal forms is equal to n to the power n minus 1. And this is precisely the dimension of the multilinear part of the of the operad of right symmetric algebras. And this shows that we can stop here, that we obtain the Grobner-Kirchhoff basis, because normal forms, in general, a Grobner-Kirchhoff basis gives you normal forms, and an incomplete Grobner-Kirchhoff basis gives you an upper bound on normal forms. So since your upper bound is correct, is sharp, there is no room for further elements of the Grobner-Kirchhoff basis.
It's already the known basis of
Yes. So, and this is equal to the dimension of Preli of n. Yeah. So this is a Grobner-Kirchhoff basis. Now we can play the same game as before, but for right modules. I am now saying that if look at these trees, there is the leading term of the Jacobi identity. This doesn't contain any Lie brackets, And here we only have Lie brackets at the root. So somehow every normal form is uniquely obtained as substitution of Lie monomials into normal forms where the top level vertices are not Lie brackets. So these leading terms prove the freeness as a right module. Okay, now I still have about 15 minutes. Are there any questions about that? So this was somehow, so I really wanted to give you this very concrete illustration because I find it's a nice blend that shows different things that you can do, that you can somehow, that you change the structure operations, you use these kind of arguments which allow you to not do the full diamond lemma computation but stop at some point when you get the correct estimate on the dimensions. So all these things are actually what on various occasions in the past 10 years I have been doing when proving things in using these methods. So are there any questions about what happened so far? Okay, then let me tell you in the remaining minutes how to deal with PBW theorems for multiplicative universal enveloping algebras, which is kind of similar story but slightly different one. Yes, fully admissible, the story is very, all this is highly trivial because fully admissible, once you change the operations like that, the Lie admissibility becomes the Jacobi identity. So you immediately see that whatever Grobner base you know for the operad Lie, it proves freeness as a left module, as a right module. Yeah, so fully admissible, the story. This approach gives you a one-line proof. You don't need all these all these things. So when we talk about universal multiplicative enveloping algebras, this means, so for example, if you are dealing with a variety of algebras with one binary operation, this means that you take an algebra A and you consider the algebra U. Let me put multiplicative of A, which is an associative algebra generated by the operators of left and right multiplication by elements of A, but sort of generated in an abstract way. So not just A, for example, acting on itself, A acting somewhere. So somehow there is a notion of a bimodule over an algebra in the context of varieties of algebras. And this definition of the universal multiplicative envelope is given in such a way that left modules over U multiplicative of A are the same as bimodules over A in the context or in the classical context of the ring theory. Now, how to explain this operatically? Suppose that we have O and operad encoding our varieties of algebras. And then I am going to define a very useful construction, which is often denoted by D of O. So this is the linear species, defined as D of O, to evaluate D of O on a finite set I. You evaluate O on the disjoint union of I with one new element, which I'm going to denote star. So what does this mean? This means that, maybe I should also write that on the level of symmetric sequences, D of O of n is O of n plus 1, which you restrict the Sn plus 1 to Sn. So somehow you have an operation with n plus 1 arguments. You now say that one argument is special, is frozen, is never going to be used, and all others we still use, we still permute. We make one argument special. So from this viewpoint, we just denote this argument as star. From this point of view, we restrict to Sn. Now, what structures does D of O have? First, it has a structure of a right O module. So we have our operations. So we have one special argument star that we don't touch. And in all other arguments, we can substitute. We can use the fact that O is an operad, so we can do the substitution. So of course, we have a right O module structure. Note that we don't have a left module structure.
You substitute, the star will disappear.
No. We don't substitute into star. We substitute in everything except for star.
You contain star.
Yes. But we don't have a left O module, because if we substitute two different things like that, we will get two different stars. So we will get an element of different nature. So somehow we have a right O module, and we also have some kind of associative operation, meaning the following, that if you have one guy like that and another guy like that, you can substitute another into star. And substitutions like that are just substitutions one on top of another, so it's really some kind of associative operation in the very literal way. Substitution into this star argument. So it turns out that the universal multiplicative enveloping algebra of an algebra A is isomorphic to D of O, circle O, and as before we have EA. So how to think about this formula? So it's kind of similar to what we've been doing for functors of change of operations. So D of O is a right O module. EA is a left O module because A is an algebra, so we can take this composite product over O, and this means that this right O module structure doesn't touch star. So star symbolizes that general element of a bimodule to which we are going to apply all the operations RA and the product over O says that if we can compute something in our algebra A, we do compute in our algebra A. So somehow, if you think a little bit what this means, it should somehow become relatively convincing. So as long as you think of star as this unknown element of a general A bimodule. So then, of course, every tree that contains one star is precisely what is obtained by applying to this element of a bimodule many different operations RA and LA. So somehow this is the formalization of this story. Now, conclusion.
One generated A.
Yes, that is also exactly the case. Conclusion. Well, there is a PBW type result for the multiplicative enveloping algebras in the same way as yesterday. So that the underlying vector space, the underlying vector space is obtained by applying some end functor to the underlying vector space of A with certain functorialities, if and only if D of O is free as a right O module. Now, in the remaining 2 minutes, let me just tell you how to check that. Because D of O is no longer an operad, so what exactly is the Grobner-Cherchov type machinery we can apply? So, first of all, we need to move to the universe of shuffle operads. So in the world of symmetric operads, we add this star. In the world of shuffle operads, we work with finite ordered, totally ordered sets. We need to make some choices. It turns out that you can make a very convenient choice. You can add this operation star to be the minimum of your set. So somehow in the shuffle world, can assume that star is the minimal element. So we're looking at typical shuffle trees that we are now interested in will be looking like this. There will be the minimal element star, and there will be some other elements. And if O has a Grobner-Cherchov basis where all leading terms are like this, so meaning that they grow, that they are shuffled trees that grow strictly to the left. There is no moment when they turn to the right. If all the leading terms are of this shape, then D of O with forgotten shuffle D of O is a free right OU module, because for D of O we're looking at the minimal leaf here, and now I am just saying that because of this condition on the leading terms, substitution in if we have a so if we look at let me put it like that. Every normal form for O is uniquely factorized as normal form that grows directly to the left with absolutely anything substituted in all the slots except for the first one. And that follows from the fact that the only constraints are of this type. So if we substitute something in creating right growing tree, it does not break the normal form condition. So maybe to be more concrete, let me consider very simply the operad O, just the Lie operad. Then there is, so if we choose this as the leading term of the Jacobi identity, then the Jacobi identity forms a Grobner basis. What are the normal forms that strictly grow to the left? The normal forms that strictly go to the left is 1, and here you have n minus 1, 2. So since we prohibited the leading term where we have an increase here, we must have strictly decreasing sequence. So we have just one normal form like that. And then, so the D is equal to something composed with Lie. So now in all the terms, so this 1 becomes star, and in all these terms we can substitute whatever we want to substitute. And of course, in every arity we have just one element. So in fact, as species, it's circle Lie, because somehow it's the operad, the underlying species of the operad of commutative associative algebras. It's a trivial representation in each arity. And in this way, you recognize another very well-known Poincaré Birkhoff Witt theorem. So for Lie algebras, there are two things that magically coincide. The universal enveloping algebra for the arising from as the left adjoint of the functor A minus, and the universal enveloping multiplicative algebra, they coincide. It's a very rare coincidence. And this shows you the Poincaré Birkhoff Witt theorem for universal multiplicative envelope of Lie algebras, that the universal multiplicative envelope looks like the symmetric algebra of the Lie algebra. Okay, I should stop here. Thank you for your patience.
Just want to say that different talks and so on, this problem of describing. I asked about the description of varieties which satisfy this property, which are PVW, such that the universal multiplicative algebra has PVW property. Some examples.
Yes. I'm sorry. I actually also should remark that this conclusion, which ultimately relies on my work with Pedro Tamarov, but this particular conclusion for universal multiplicative envelopes, this was observed and developed by Anton Haroshkin several years ago, but yeah. So I should have mentioned the.
No, I formulated it not in operator terms, but in terms of success previously.
Yes.
Yesterday,
Yes.
The question was exactly after your result, especially before your result I was asking, but after your result I was asking how, and it should have some interpretation in terms of operators. Any more questions?